All right, so we're going to work through two more examples of graphing rational functions. So for number 3, we have the function r of x equal to 6x squared minus 7x minus 3 over 2x squared minus 7x plus 6. So I'm going to work through first to check and see if this rational function is written in lowest terms. So I'm going to factor both the numerator and denominator. So to factor the numerator, I'm going to multiply the constant -3 times the leading coefficient 6, which gives me -18. That number goes on top, -7 goes on bottom. So I'm looking for two numbers that multiply to give -18 and add to give -7, which are -9 and 2 respectively. Okay, so I can take the middle term, -7x, and split it into two terms using those coefficients. And then I'm going to factor this resulting quadratic by grouping. So I can factor a 3x out of the first two terms, which leaves me with 2x minus 3, and a positive 1 out of the last two terms, which leaves me with 2x minus 3. So 2x minus 3 is the common factor. And then when I factor that out, that leaves me with 3x plus 1. Okay, so that is how we factor the numerator. Okay, we're going to do the same thing to factor the denominator. So again, I make my x. The number that goes on top is 6 times 2, which is 12. The number that goes on bottom is -7. So I'm looking for two numbers that multiply to give 12 and add to give -7, which are -3 and -4 respectively. So I'm going to break the middle term up into two terms using those coefficients. And then we're going to factor the resulting quadratic by grouping. So I can factor an x out of the first two terms, leaving me with 2x minus 3. And then I can factor a -2 out of the next two terms, leaving me with 2x minus 3. So 2x minus 3 is the common factor. And when I factor that out, that leaves me with x minus 2. Okay, so that right there is that rational function factored completely. And when we look at that, we see that it's not in lowest terms because we have that factor of 2x minus 3 in common. Okay, so given what we know about rational functions, that tells us that this rational function is going to have a whole. We'll take a look at how we find the coordinates of that whole in a second. Okay, so in lowest terms, the rational function is 3x plus 1 over x minus 2. Okay, so then we're going to work through our 6-step process. So step 1 is to find the domain. So the values that make our denominator 0 are 3/2 and 2. So we know x can't be equal to those two quantities. Number 2, our intercepts. So the x-intercepts are the zeros of the numerator in lowest terms. Okay, so the only value that makes the numerator 0 in lowest terms is -1/3. So that's going to be the ordered pair -1/3 comma 0. And because the multiplicity of that 0 in the numerator is odd, that tells me that the graph is going to cross the x-axis at that point. Okay, for the y-intercept, we plug 0 in the place of x and solve for y. It doesn't matter if you plug into the original function or the simplified function. Your y-intercept is still going to be the ordered pair 0, -1/2. Okay, step 3 is to test for symmetry. Again, it doesn't matter if you plug into the original function or the simplified function. I'm going to plug into the original function. We get 6x squared plus 7x minus 3 over 2x squared plus 7x plus 6. And that's neither the original function nor the opposite of the original function. So this has no symmetry. It is neither even nor odd. Okay, step 4 is to find the asymptotes. So the vertical asymptotes are going to be the zeros of the denominator in lowest terms. So that's going to be the line x is equal to 2. This has a horizontal asymptote. So again, like you can do this in the original function or the simplified function, it doesn't matter. But if, let's say I do the simplified function, okay, the degree on top is 1, the degree on bottom is 1. So the line y is equal to the ratio of the leading coefficients. So 3 divided by 1. The line y is equal to 3 is a horizontal asymptote. And then if we want to find the coordinates of the whole, the x coordinate is going to be the value that makes your simplified factor, the canceled factor 0. So the value that makes 2x minus 3 equal to 0 is when x is equal to 3 halves. And then we're going to plug 3 halves into the simplified function to see what the output is. So that's going to be 3 times 3 halves, which is 9 halves, plus 1 over 3 halves minus 2. And then again, we have a complex rational expression there. So I'm going to multiply the numerator and denominator by the common denominator of the smaller fractions, which is going to be 2. So that's going to make 9 halves times 2, which is 9, plus 2 over 3 minus 4. So that's going to wind up making the y-coordinate of the whole negative 11. Okay. What we want to do next is we want to make our table. So that's going to be step 5, is to make our table. So the values that go on our table are our x-intercepts, vertical asymptotes, and holes. And we want to list those in order from smallest to largest. So the smallest value is negative 1/3. The next smallest value is 3 halves, and the biggest value is 2. And those three numbers divide our number line up into 4 intervals. So the first one is from negative infinity to negative 1/3. The second one is from negative 1/3 to 3 halves. The third one is from 3 halves to 2. And the fourth one is from 2 to infinity. Okay, so we want to pick a value on each of these intervals. So I think the best choice to pick on the first interval is negative 1. I'm not going to work through the calculations for this. You guys can figure this out. But when we plug negative 1 into the function, we should get 2/3 as an output. On the next interval from negative 1/3 to 3 halves, I don't want to pick 0 because we already know that that's our y-intercept. So I'm going to pick r's value at 1 on that interval. So when I plug 1 in, that gives me an output of negative 4. And then on the interval from 3 halves to 2, so that's 1.5 to 2, I'm going to pick the decimal like 1.75. So as a fraction, that is going to be 7/4. And r's value at 7/4 is negative 25. And then on the last interval, I'm going to pick 3. So r of 3 is going to be equal to 10. Okay, so once we have that, we're going to go ahead and draw the graph of our rational function. Okay, now what I want to do for this graph, I don't want to draw like 10 dash marks going up and 25 dash marks going down. Okay, so I'm going to adjust the scale of my graph in the y direction, where each dash mark in the y direction is going to represent 3 units. So I just have to make 4 dash marks going up to get to that value of 10. And then I have to make 9 dash marks going down to get to the y value of negative 25. And then I'm going to keep my scale in the x direction 1. Okay, so we're going to plot our information from steps 2 and 4. Okay, so we have an x-intercept at negative 1/3, 0, which is that point right there. We have a y-intercept at 0, negative 1/2. Okay, so again, don't forget your scale in the y direction is 3. So 0, negative 1/2 is going to be like somewhere in there. We have a vertical asymptote at x is equal to 2. So I'm going to go ahead and dash that in. We have a horizontal asymptote at y is equal to 3. So again, be mindful of your scale there. Then we have a hole at the ordered pair 3/2 negative 11. So we're going to go to 1.5 negative 11, which is going to be like down in here. So we're going to have a hole at that point. And then I'm going to take the values from my table and plot those as well. Okay, so we have the ordered pair negative 1 2/3, which is going to be about in here. We have the ordered pair 1 negative 4, which is about in there. 7/4 negative 25, which is going to be like in here. And the ordered pair 3/10, which is going to be about right there. And that's more than enough information for us to sketch the graph. Again, like I like working around the x-intercept first. So the multiplicity of the 0 on top is 1. The graph crosses the x-axis at that point, which it does. And then I'm just going to kind of follow these points here going down like that, and like that. And we know that as we approach the vertical asymptote from the left, because the only x-intercept occurs at negative 1/3, that's going to force that part of the graph to go to negative infinity. Okay, the multiplicity for the 0 on bottom is odd, which means the graph has to go in opposite directions at the vertical asymptote. So as we approach the vertical asymptote from the right, the graph has to go to infinity. And then we're going to draw our graph passing through that point. And then what's going to dictate the end behavior of this graph is the horizontal asymptote. So as the x values go to negative infinity, the graph has to approach the horizontal asymptote. And as the x values go to infinity, again, the graph has to approach the horizontal asymptote. Okay, so that right there is going to be the graph of the rational function for number 3. Okay, let's do number 4. So for number 4, we have the rational function r of x equal to x minus 1 over x. So again, this rational function here doesn't look like the other ones that we've looked at. Okay, the rational functions that we've looked at have been combined into a single fraction. So I want to combine this into a single fraction. So if I get a common denominator of x, this rational function becomes x squared minus 1 over x. And then I want to check and see if this is in lowest terms. So the numerator factors to x plus 1 times x minus 1 all over x. Okay, so that is in lowest terms. All right, so we're just going to work through our steps here really quickly. So for number 1, the domain is the set of x such that x can't be equal to 0. Number 2, the intercepts. So the x-intercepts are the zeros of the numerator in lowest terms, which are the ordered pair negative 1, 0 and 1, 0. And the graph is going to cross the x-axis at both of those points because the multiplicity of those zeros are odd. Okay, the y-intercept. If we plug 0 in the place of x and solve for y, we get negative 1 over 0, which is undefined. So there is no y-intercept. Step 3 is to test for symmetry. So when we take r's value at negative x, that's going to be x squared minus 1 over negative x. So that gives us the opposite of our function, which means that the function here is odd, thereby having origin symmetry. Okay, so we need to be mindful of that whenever we make our table values. Okay, if we choose them wisely, we're going to get additional points on the graph of our function. Okay, for the asymptotes, so this has a vertical asymptote where our denominator is 0 in lowest terms, which is at x is equal to 0. Because the degree on top is 1 larger than the degree on bottom, the graph is going to have an oblique asymptote. So for us to find the oblique asymptote, we have to long divide the denominator into the numerator. Okay, and again, we have to put 0 as the coefficient for the missing term. So what times x gives us x squared? Well, that's x. When I distribute x across both terms, we get x squared plus 0x. And then when I subtract, we get 0x minus 1. And x times 0 gives me 0x. So my oblique asymptote here, and again, I don't have to worry about the remainder. It doesn't matter. Our oblique asymptote is the line y is equal to x. Okay, so step 5, we're going to make our table. So the values that go on our table are the x-intercepts, vertical asymptotes, and holes. There aren't any holes here. So our x-intercepts are -1, 0, and 1. So again, our x-intercepts are -1 and 1, and our vertical asymptote is 0. So those 3 values split the number line up into 4 intervals. The first one is from -infinity to -1. Second one is from -1 to 0. The third one is from 0 to 1. And the fourth one is from 1 to infinity. Okay, and again, because this function has symmetry, we want to choose these values wisely. Okay, so the value I'm going to pick on the first interval is going to be r of -2. And when you find r of -2, you're going to get that equal to -3/2. The value that we're going to pick on the next interval is going to be r of -1/2. Like I have to pick a fraction on that interval. Okay, so r of -1/2 winds up being +3/2. On the third interval, from 0 to 1, like I don't want to pick r of 1/2, because if I know what r's value at -1/2 is, and I know that the function has origin symmetry, I can take the opposite of both of those coordinates, and that's going to give me r's value at 1/2. So what I'm going to do instead is I'm going to pick r's value at 1/4. Okay, so when we pick r's value at 1/4, I got that to be -15/4. And then the last interval, I don't want to pick r's value at +2, because if I know r's value at -2, I can take the opposite of both coordinates and get r's value at +2. So I'm going to take r's value at 3 instead, and that's going to be equal to 8/3. Okay, so once I have that, I'm going to go ahead and sketch the graph of the rational function. So I'm going to make a coordinate plane that goes, let's say, 4 units in each direction. Okay, so we're going to plot the information from steps 2 and 4. So we have x-intercepts at -1, 0, and 1, 0. And then we have a vertical asymptote at x is equal to 0, which is the y-axis. So I'm going to dash in that vertical asymptote. And then we have an oblique asymptote at y is equal to x. So I'm going to go ahead and dash that in as well. Okay, and then we're going to take the points from our table and plot those. Okay, so we have the ordered pair -2, -3/2, which is that point right there. And because the graph has symmetry, then the ordered pair 2, +3/2 is going to be on the graph as well. Okay, because it has origin symmetry, I just take the opposite of both the x and y coordinates in my table. Okay, we have the ordered pair -1/2, 3/2, which is going to be that point right there. And if I take the opposite of both coordinates, that's going to be 1/2, -3/2, which is going to be that point. We have 1/4, -15/4. So that's 1/4, -3 3/4, which is going to be about right there. And when I take the opposite of both coordinates, we get negative 1/4, positive 15 over 4, which is going to put that point about right there. And then we have the ordered pair 3 8/3, which is 3 2 2/3, which is going to put that point in there. And when I take the opposite of both coordinates, that gives me negative 3 negative 8/3, which is going to put that point about in here. Okay, so again, because we chose our points wisely, not only did we get 4 additional points on the graph, we get 8 additional points on the graph, which makes it really easy to graph this. So I'm going to start with the intercepts. So it looks like the graph is going to cross the x-axis at both of these points, which that makes sense because the multiplicity of both of those zeros is 1, it's odd. And then I'm going to draw my graph towards the asymptotes next. So I'm going to go to the vertical asymptote first. So it looks like as we approach the vertical asymptote from the right, the graph goes down to negative infinity. When we approach the vertical asymptote from the left, the graph goes to positive infinity. And that makes sense because the multiplicity of the 0 in our denominator is odd. So the graph should be going in opposite directions as we approach the vertical asymptote. Okay, and then we're going to go extend out to these 2 points right here. And then the end behavior of our graph is dictated by the oblique asymptote. So we're going to draw our graph approaching the oblique asymptote as the x values go to infinity, and approaching the oblique asymptote as the x values go to negative infinity. Okay, so that right there is the graph of that rational function. And I think these 4 examples are a pretty good representation of the different situations that you can run into when graphing rational functions. So we had an example with an oblique asymptote, we had an example with a hole, we had an example that had no horizontal or oblique asymptote, but we could determine the end behavior by doing long division. So I think this is a pretty good representation of like the situations that you can run into when graphing rational functions. Okay, so that's going to wrap up this part of the video, and then I have 2 more examples to look at in the next video where we're going to work through the process backwards. So here, with these examples, we were given the function and asked to graph the rational function. In the next 2 examples we're going to look at, we're going to be given the graph of a rational function and asked to come up with a function that yields that graph. So we'll take a look at the process that we use to determine that.